Circular Motion Practice number 10 from the Circular Motion Practice Honors Conceptual Physics 9th grade worksheet. This was assigned for homework. It's about a rubber stopper spun in a vertical circle. First task is to get the linear speed using 2 pi r over t, and you get 11 meters per second squared. R is the radius. T is the time it took to make one revolution, and the revolution is the circumference, so it's 2 pi r. So you get 11 meters per second. That's the linear speed. It's also the tangential velocity. In the next part, it asks you for the net force on the stopper, and by definition, centripetal force is a net force. And I said this a lot in class, but a good way of saying this is that this net force that we've calculated, this represents the amount of force at any given time that is necessary to make that particular stopper go at that particular speed and with that particular mass and that particular radius size circle. So this is really a general expression in the similar way that F net is a general term for all of the forces on the object. And in this case, it's like the force that you need to supply to the object to make it go in a circle. Again, remember to pause. If something doesn't make sense, you can go back and listen to it again and again. This is the diagram of the forces on it at the top, at the peak. Now, if you picture a rubber stopper going around in a circle, there's a tension pulling it down. There's a tension pulling it down right here. There's also a weight pulling it down. Weight always pulls it down. That force right there on the left is the weight. I don't know which is greater. It doesn't really matter. I think it actually turns out that the weight is less, which would make that correct. But what matters is that you realize they're both down, because then you can write the following. But before I reveal this, I'm going to move this rectangle around and I'm going to reveal what's underneath there. But before we worry about that, just think about this for a second. If this is the net force right here, if this is the net force, what that means is these two added up have to equal that. That's it. It's that simple. So if I can calculate this weight, if I can calculate that weight, it's really easy to figure out what the tension is. So I'm just going to calculate the weight and then figure out what the tension is. So I know that the net force is those two added together. That's what this equation right here is simply saying, that the net force is those two added together. That's the 4.75 is the net force. Calculate the weight using force weight equals mg. I believe I multiplied by 9.8 in this case. I took the mass of 0.055, which you also use here. I took that mass and I multiplied by 9.8, and that got me this weight down here. Okay, that got me that weight. So now I just figure out the tension, because 4.2 plus 0.54 gets me back to 4.75, roughly speaking. So I calculated the tension at the top. The tension at the bottom has to be greater, because as you can see in this diagram, the tension at the bottom, the tension at the top, the tension at the bottom has to be greater, because this force minus this force equals that total. Now, how do I know that? I know that because it goes back to this. This is the force that I always need at all times toward the center. So if I have this force going away from the center, I have to compensate for that. I used the analogy in class today of, this would be the person that in your group is a slacker. So this person has to work extra hard to make up for the slacker. And what are they trying to make up for? What are they trying to accomplish? They're trying to accomplish a force of 4.75. So the tension minus 0.54 has to equal that. So when you plug in, you get 5.3 newtons.